Okay, I think we can get started here. So welcome to the AI Generative Workshop, the Caravel Overview and Q&A webinar. Just a reminder that all questions, please submit through the Q&A function and not the chat button. So the speaker today is Jeff DiCopo. Jeff, if you can please introduce yourself and get started, that'll be great. Thank you.
Great, thank you. So thanks, Andrea. So I'm Jeff DiCorpo with Efabless. I'm responsible for I serve as a general manager, so I'm responsible for a lot of activity around the Chip Ignite solution, program management, getting into feature set, and kind of making that program operate kind of within the Efabless within our Efabless company. So today I'm going to walk through a little bit on an overview of Caravel itself, right, and also how to integrate a design, as well as kind of how to successfully submit that on the Efabless platform for tape out. All right, so to begin with, I'm going to start with a little bit of overview of Caravel itself, and what I have in this as we go through today's structures, I have a number of videos that I'm going to be referencing and using and leveraging that kind of demonstrate and walk through various steps. I'm going to I'll share my screen here. But if you are interested in finding those after the tutorial, you can find those from our website. The best way to get to them is go to our homepage, efabless.com, and then press the Get Start button. The Get Start button will bring you the kind of the first sequence of videos that some of these we're going to be leveraging, or we'll be going through parts of those. We're also going to be obviously handling some Q&A as we go through it. But this first step basically provides an overview of Caravel, as well as kind of getting started with your desktop and getting the kind of dependencies and tools installed that you need, as well as getting your project started in terms of a repository, and then finally uploading and submitting your project to the Efabless platform. There's another sequence of videos that we're also going to be referencing, and you can find those kind of through a link at the top of this page. It's right here, and if you go to that, you'll see an example digital design implemented in Caravel, where we go through the steps of taking a simple counter timer kind of design example and integrate that into Caravel. We go through the steps of actually configuring that, running RTL verification and physical implementation, and then the current final video in this series is just basically reviewing your design using K-Layout. And so we'll touch on all of that. There'll be some additional videos that will be posted shortly that are going to go through some additional steps in terms of sign-off verification review, and that will be coming soon. But this, hopefully by the end of at the end of this webinar, you're going to have a pretty good sense of kind of what the overall process looks like, and how to implement a design, integrate a digital design once you already have kind of your RTL, how to integrate that into Caravel, and run OpenLane to implement that physically. Also, as well as run verification, RTL verification for it if you're doing that. Using our tools or flow, and then also how to submit that on the Efabless platform. Okay, so I'm going to go ahead and start with kind of first step, which is just to provide a little bit of an overview of Caravel itself. I'll run through a quick little clip to start with, and then we'll kind of break out of that and maybe answer and provide some additional color, answer some questions via the Q&A chat again. As Andrea mentioned, if you have questions, please use the Q&A facility kind of in Zoom to post your questions, and then we'll be pausing periodically to review and answer those during the session. Right. So I apologize.
The only way to do it is to automate it. What Zapier allows us to do is connect to our customers' Shopify chip.
Yeah, so we're going to have we may get a few advertisements as we go, but hopefully that should be minimal.
Caravel is an open source template for a system on chip, or SoC, which provides the needed infrastructure for designs using Chip Ignite.
All right, just to pause there. Is audio coming through, Andrea, from the video?
Yes, yes.
Great.
The Caravel chip is based on the Skywater 130 nanometer open source PDK. There's a version of Caravel called Caravan, which provides bare I/O pads for designs with high speed, high voltage, or negative voltage signals. In this tutorial, we are going to focus on the standard version of Caravel. Caravel's architecture consists of a pad frame, a management area, and a user's project area. Users place their designs in the user's area and use the management area and the pad frame to enable communication of their designs with the outer world. The management area implements a RISC-V based SoC that includes a number of peripherals like timers, UART, and GPIO. The management area runs firmware that can be used to configure user project I/O pads, as well as observe and control user project signals through on-chip logic analyzer probes, and finally, control the user project power supply. The users area, which is also called user project wrapper, has dimensions of 2.92 by 3.52 millimeters, which is approximately 10 millimeters square of silicon area. This is about 2/3 of the area of the whole chip. It has access to 4 power supply domains, as well as 38 I/O pads, which can be configured through firmware running on the management SoC. It also has 128 logic analyzer probes used to control and observe signals. It has a wishbone port connection to the management SoC wishbone bus. If you would like to see how to implement a design using
Okay, great. So just to review or recap a little bit on some of the key points there, I have a couple slides from that graphic. So the key points for integrating or for implementing your design using Caravel, at a very high level, there's a user project area. The process is you build, you create, generate your design via in RTL. We run OpenLane to implement that and provide a GDS for a macro, which represents the user project area in this design. And then there's a final step where you submit that on our platform, and that gets integrated with a golden copy of Caravel, which basically brings in the pad frame and all the infrastructure for the rest of the chip. Right, so within that includes all the power, pad frame and power infrastructure, but it also includes a management area that includes a management SoC with a RISC-V processor and provides a bunch of features that you can integrate with and utilize as part of your design. Right, and really key to that is obviously the 38 configurable GPIO that are around the pad frame. They kind of start, I'll just kind of describe it here. You can find this in the documentation, but GPIO 0 is on the bottom right, and that wraps around the top of the chip all the way through IO 37 on the left. And then there is a wishbone bus, a set of ports. There's basically ports at the edge of the user project wrapper that you integrate to connect to those IO. And we're going to talk a little bit about that when we talk about integration. There's a wishbone bus that is extended from the management area along the bottom, right? And that wishbone bus can be used for either providing a clock for your design if you want to run off the core clock that's provided for Caravel. There's also a reset signal there, which you can integrate and utilize in your design. In addition, there's the kind of the address, the rest of the bus address, where you can run basically implement your project as a slave for to the CPU that's within the management area in Caravel. And so you can drive and read and write registers, for example, on a device that you implement there. Kind of in addition, there's a couple other features if you're interested, and you can find those in the documentation. There's some IRQ signals for interrupting the processor from your project area. There's also a user-defined clock, which you can configure from the management area if you want something outside of the core clock frequency, right? And then other kind of key points there is a set of logic analyzer ports. Those are described, I think, in the see right here in this diagram, right? So there's a set of logic analyzer probes. There's 128 of those that basically run from the management area to the user area. You can connect to those to kind of monitor or probe or drive signals to your project. and they're a 3-wire interface. So there's an input and output and an enable signal for those, similar to the GPIOs, which we'll talk about a little bit later, right? And I think it was power domains, right? So then the other just comment is there's up to 4 power domains, 2 digital and 2 analog. If for simple designs, you're primarily connecting to the single digital power domain for OpenLane. So that's what kind of by default OpenLane will connect to and utilize, but you can connect to these other domains as well if you have a need based on your design requirements. All right, so let me pause there and check on questions. Also, if any other comments from anybody on the team too, if anything I missed, I should cover. Appreciate that. All right, so how do we input 5 volt to the chip? SkyWater provides 5 volt devices as well as 3.3 volt supply support for 5 volt as well. Andy, do you want to pick that one up? Are you online?
I'm having trouble getting to the window. Give me 2 seconds. How do we input 5 volt to the chip? SkyWater provides 5 volt devices as well as 3.3 support for 5 volt as well. So we have in the Caravel IO, not in the total library that exists in Sky 130, we have 3.3 volt IOs that are over voltage tolerant up to a certain level. So you can stress the IO up to a higher voltage. There's also a dedicated high voltage IO, a 5 volt compliant over voltage IO that's intended to be used for things like I2C, and that is not currently the IO that's on Caravel. So the GPIO that's on Caravel, that data sheet is in user read the docs, and that is a VDD IO domain rather than the core supply domain for the user project. Right now, we're connecting those 2 things together almost all the time. So it's very, very rare that we've had somebody who's tried to separate the IO domain from the core domain. And I don't know if that completely answers your question to Samarth, but very hard to do today on Caravel.
Okay, thanks, Andy. Next question is, does the wishbone connection from the management area will help to provide continuous data to user project? Assuming an accelerator implemented on the user project. Yeah, so that is one. So if you're implementing an accelerator, so one model is to implement that accelerator and connect it onto the wishbone bus, and then run traffic to it from the management area. So as one model you could implement for with an accelerator and integrating that into the Caravel design. So if we had answered that covers that one. Please post again if we missed something or you need further clarification on any of these. Is the AI generated design contest paid? So the design contest for the for AI generated designs, we are the fabrication, the selected projects or the winning projects that are selected from the contest. We are running fabrication for that. We're sponsoring fabrication for that. So that is at no cost to the submitter, right? So that is a sponsored funded fabrication run without, no cost associated with that for the submitter.
We are not compensating the contestants.
Correct, but there's no other compensation outside of that to the contestants or participants. What is a wishbone bus? So wishbone bus is a standard, bus interface, CPU system bus interface. It's open standard, and it's the one kind of dominantly, kind of very commonly used in open source SoC designs. You'll find it. There's quite a bit of documentation on that you can find in the public domain. We can probably provide some references or pointers to that kind of after the webinar, so you can learn a little bit more about it. Okay, so next question. I missed when you said this, but what is the interface between the RISC-V core and the user design? Yeah, so there's several options there, right? So the one of them is the wishbone bus I just mentioned. So that is a system bus that is, the CPU sits on, talks to the peripherals within the management area, as well as it extends that same interface out into the user area, where you can implement a slave device in your design on that bus, and can talk to one or more of those actually sets of devices through that bus interface. And so that's one option. The other option is through the logic analyzer probes that I mentioned, right? So there's a set of 128 logic analyzer probes that provide just the ability to kind of directly monitor or drive signals to your project. And that would be all under the control of the RISC-V processor that you would, and so you would implement firmware then to drive that functionality when you're operating your design. Okay. Next question: is there an existing firmware that runs on Caravel RISC-V core? Yes. So there is a GitHub repository. I'll show you it real quickly here. So if you go to the GitHub Efabless. So you go to Efabless organization under github.com. That's where we host all of our GitHub, our repos for Caravel and for the ChipIgnite. There's one here called Caravel board right here, Caravel_board. This repo contains both all the kind of assets related to both the hardware and evaluation boards and that we provide for doing silicon bring up and turn on. It also provides a set of firmware examples for that implement that exercise various features around Caravel, and provide examples for how to implement your own test benches or create your own test benches for your design. It also provides tools for programming the Flash. That's connected. That's on our development boards, are connected to the Flash interface on Caravel. All right. Next question. Can we generate area, power, and delay report for any RTL using this? There are a series of reports generated as part of OpenLane. A lot of that is documented in the OpenLane repository and documentation set. So again, that's also can be found by going to our organization or github.com. There is a OpenLane. I believe we still have an OpenLane fork here. Yeah, so there's a fork of the OpenLane, the primary OpenLane repo that sits under the Open Road organization. But this has all the documentation for OpenLane and provides you a lot of details in terms of reporting and kind of a lot of the specifics of the reporting that's provided as part of the flow.
So to address tactically the question, the answer is yes to delay, yes to power, although I believe by default that it's turned off. And I think that the current answer is no to area. I will say that you won't get it for RTL. You've got to go through the synthesis process to get those answers. So you've got to run the flow, go through synthesis to get the delay and the power report. And I think that power is by default turned off. And I don't remember seeing an area report, but you can get gate counts.
Okay, thanks, Andy. So so moving on to the next one, is a comment about please organize a similar webinar on Caravan for analog only designs, very little support available for it. So noted, and we are doing work on providing more content around the analog flow and more support for that. And that will be coming. Sorry to cut you out when you were talking about accelerator model design comments. Can you repeat that? Oh, I cut out during the accelerator model. So my comment on, I think there was a question around can you drive an accelerator function or macro from the RISC-V core, and is the wishbone bus suitable to do that? And I was commenting that is a model that is one model that would work, or that would be recommended, right? So it would be to implement your accelerator function and then implement the register set around that, or digital wrap around that then connects to the wishbone bus so that you can drive, or you can both provide data in and read data out from to that macro.
Elaborating just a little bit more, you will be able to drive the accelerator, but it won't be super efficient. So you can get data to your accelerator, you can provide your accelerator function. It'll be more efficient than running the function in software on the CPU. But if you want to run an accelerator with very high efficiency, you're going to want a local memory that you stuff with data, and then you run it in some kind of burst fashion, and then you shut it off. So that's if you're trying to power optimize, you're going to want to localize the data near the accelerator rather than using the CPU to feed it.
Okay. So if you have further questions, please add or post again on that one. Okay, next question is it possible to instantiate a DRAM or SRAM in the user area? Any estimates on the possible capacity estimates? It is possible to install a SRAM today. We have some SRAM macros that are used inside of that have been posted and used within various designs that are posted in the community. You can find examples of those on our site, right? So just to give you a quick pointer for that, if you were to go to, I bet you I'm going to have to go into let me bring up an incognito window just for this. I have an issue logging in directly. So I'm going to just log into this is logging into going through the registration process from our platform and logging into the site. If you go to our site, you'll find a number of public projects posted here under projects, public projects, and you can select. I would recommend select all, and you'll see a variety of designs here. A number of these have implemented SRAM using an open RAM macro that's that's available publicly. We also have a DFF RAM macro that is provides synthesized memory macro that is also an option that you could implement. And I think the other question is any estimates on the possible capacity estimates roughly. I think go ahead.
I'll take that one. I think the largest memory that anybody's instantiated to date is 8 instances of a 2K macro. That's the largest one that I'm aware of. Now there might be something larger than that, but the issue we have right now is that we don't have a very large macro in place that somebody's proven on silicon yet. So there's no 4 or 8K RAM macro yet that somebody's proven in silicon for us to do a larger kind of bank-based memory in. Hope that answers the question. And in terms of DRAM, no, it's not possible. There's no current embedded DRAM. If you meant DPRAM, as in dual port, yes, there is a dual port cell, and there are dual port memories in the IP set that's already public. So there's a DP macro is one of the IPs that I think from Open RAM has already been brought out, and it's in the community. I think that was developed by Matt Goodhouse in Santa Cruz, UC Santa Cruz.
Yeah, and I think that if you go to our, I believe again on our GitHub, if you look up, I think it's SRAM, Open RAM. There's an Open RAM project. This one right here. So there's a Sky 130 SRAM macros, which I'm bringing up a little slowly. But this has a number of existing macros from 1 to looks like there's a 16K one in here, which I'm kind of surprised to see. But I know we've had 1 and 2K macros that have been used in a number of designs, and some of these other macros are kind of still in development. Some of the larger macros that are in this list, which you can find some information on those Open RAM macros there. Next question is it possible to place an eFPGA in the user area? So we have examples of that as well. In fact, Efabless did a project called Clear that is also public and posted on our website, and which you can find that implements an eFPGA. There's also a number of other projects. If you search eFPGA on our on the public projects view on our website, you'll find other examples.
Could you go to the website and do that, Jeff, just for a second? Because I think that's worthwhile. There's multiple very cool projects in the website with embedded FPGAs already. I think that's worth hitting a second.
Did you want to comment on any of those?
No, just to hit the point that it A is possible and B has been kind of actively pursued by multiple people. So not only is it possible, but it's a very interesting topic for the audience in general.
Okay, great. Okay, next, keep pressing on here. Is the repository enough to go through the whole process? Or are there any other additional tools which are needed to be used in a simple design? I'm asking as a beginner. So we do have a complete end-to-end flow, which we're going to be going through that as part of the discussion today. In fact, I probably should pause on questions and I'll pick it up again here in a bit, but I want to make sure we get through some of the next set of topics on the webinar. Okay, so let's move forward. The next thing we're going to talk through is just a quick discussion on setting up your desktop. So if you go through this, recommended if you have access to it and you're able to, definitely recommend using a Linux desktop. Something we frequently reference, and you'll find a lot of our content referencing Ubuntu 20 in particular. So if that's an option for you, you have access or you can get that set up, I'd highly recommend that. That will make your life a lot simpler. We are obviously there are other paths as well, and we're continuing to work to kind of provide additional documentation and reference and guidance for people trying to utilize other paths. There are folks that have been implementing and working with Windows WSL, based specifically using WSL. But there's some additional, gotchas and things to know about, to kind of work through that successfully. So I would point you to this video here called Setting Up Your Desktop. This walks through kind of the basics of setting up a Linux environment, and it has some references and pointers for WSL in that as well. But if you're struggling, please reach out to us and we will help provide you some guidance. I'd recommend, if you haven't already, join the Silicon Slack community, and there is a specific channel for the AI challenge, which we will highlight here in the video as well a little bit later. All right. Okay, so that's a little bit on setting up your desktop. Once you've set up your desktop, the next thing you're going to want to do is create a new repository for your project. We have, again, I'm just going to run through a couple of clips that kind of walk through that specifically.
Meet Grammarly Go, your go-to solution for getting quality work done quickly.
There we go.
Next, go to the template repository. It's called Caravel User Project. Use the link in the video description below. Click the Use This Template green button. You'll need to fill in a name and an optional description. You should pick something that helps people know what your design is. So if you're working on...
I'm going to skip that part. I think that's fairly big, pretty basic. The main thing here is you're going to want to go to the, as it's shown in the video here, you're going to want to go to the Caravel User Project repository. So this is the starting point for, and provides a template for implementing a digital design specifically through ChipIgnite using for Caravel. And it provides basically an example design in that, and it provides a kind of the wrapper framework that you need to integrate your design in order to submit it on our platform for tape out. And the primary way, the best recommended way to do that is use this green button in the top upper right, which will basically generate a new repo based off of this Caravel user project and get you kind of all the right starting point in terms of file set that you need to be successful. The next step from here, I believe this just goes to talk about, so after you're done here, you'll have a new repo kind of in your space that you'll
the best place to go is the open source.
The next step will be to clone that repo locally to your desktop, and to run setup on that. So let me go ahead and show you that real quickly.
In the repository, go to the repository you created in the previous video, click the green code button. With GitHub, you can either clone via HTTPS or SSH. Either will work, and it only makes a difference when you want to push your changes. This will depend on the Git client you use. I use SSH keys, so I'll click the SSH version. Copy the URL and go to your terminal. Type git clone, the name of your repo, and press enter. After a few minutes, you should have the new repository set up on your local computer. Now we're going to set up some environment variables. An environment variable stores some information about the setup, for example, where the ASIC tools and the PDK will be installed. An environment variable is only.
So just a note on this, we've made an update and change to the repo so that you don't need to set these environment variables. They'll be automatically set for you if you don't specify them. So the only reason you would need to specify them is if you want to install some of the dependencies for your project in another location besides the default location where it's going to put them. By default, it's going to put all these dependencies in a subdirectory under your project called dependencies. So I'm going to skip past that a little bit and just get to the part where we're doing the setup. But all this export you don't need to do anymore.
Be installed. Now we can install OpenLane and the PDK by typing make setup. It takes about 5 to 10 minutes, so I've sped up the footage here. It's a good idea to build an example project to test the tools. You can skip the following steps if you don't want to try it, but if you do have problems later, it's a good idea to come back here and run this test. Inside the OpenLane directory, you will see two subdirectories. The user project example is an example project. We can build it by just typing make user underscore proj underscore example. It takes about 30 minutes, so again, sped up the footage here. Now the project is complete and we can see that the GDS has been updated and we can load it with KLayout. I'll turn on a few of the cells so we can see more of the design inside. If you need help or support, the best place to go is the open source.
Okay, so all right, so I'm going to pause just to see if there's some additional questions on this. Okay, max frequency of Wishbone we can run on Caravel 40 megahertz. Does 40 megahertz work? Yes. Well, do you want to talk to that, Andy?
Yes is the answer.
Yes. So basically, yes. The default core clock or clock frequency that we have on our development board is 10 megahertz. But there's a clock system that you can manipulate that or modify that, including increasing it through a PLL. That's within Caravel. All right, any plans for a Caravan webinar? Yes, we will be doing something on Caravan in the future, so stay posted for that. Is it possible to work on the cloud for this project to run the flow? We've been having a lot of conversations around that, and we will want you to reach out to us. If you could on this, again, join the Slack community. I'd recommend that. And you can post a message to us for asking about kind of a cloud support capability. But we are actively working on a solution for that. The other thing you could do is that you can also just email us at shuttle@efabless.com if you prefer to reach us that way. All right, is it possible to open the OpenRoad GUI with Caravel? It is. There is documentation around how to use the OpenRoad GUI. I don't have kind of the notes here prepared to be able to speak to it, but we can address that kind of offline. Again, I'd recommend joining the Slack community and posting that question there, and we will follow up with you on that. All right, I don't see any more questions on specifically to this topic we just covered, so I'm going to go ahead and move on, and I'll come back to some of the additional questions here a little bit later in the video. So let's move on to the next topics, which is integrating RTL. So So I have so the next bit of this is going to show how to integrate, once you have an RTL that you've generated through an AI, through your AI process, then the next step will be how to integrate that into Caravel. Now you can actually use, and we've seen examples where you can actually have a lot of that done for you through generative AI process as well. But just to give you an idea of how that kind of the specifics around the interface and how you would do that manually, we'll kind of walk through that briefly to show you.
This is not just the deck of cards. This is a collection of 54 beautifully.
Okay.
This folder already contains a user's project wrapper Verilog file.
Okay, so we've cloned the project locally, and we're jumping into the RTL directory within that project that we just cloned, right, from the previous step I just talked about. And we kind of jumped into this user project wrapper.v, which is the top level macro for for implementing your design,
which is called user project wrapper.v. This file has a user project example Verilog module integrated in it, which provides ports to interface to the user's project design with Caravel. These include interfacing ports to the I/O pads, a Caravel management SoC wishbone bus slave interface port, logic analyzer ports to observe and control internal signals on the user design if needed. We can rename the user project example to user proj timer, as we will integrate our timer inside it. We start by deleting the module counter and its instantiation inside user proj timer, which we are not going to use in our project. Also, delete the example logic that we are not going to use. Then we instantiate the module timer and connect its clock and reset ports to those of the user proj timer. So the clock port is connected to WB_clock_I, and the reset is connected to WB_RST_I. For the 7seg 8-bit signals and the digital enable 4-bit ports, we need to connect them to 12 of the 38 Caravel I/O pads. Every I/O pad is associated with 3 ports. For example, I/O pad number 5 is associated with the ports IO_in 5, IO_out 5, and IO_OEB 5. The IO_OEB controls the direction of the signal. 0 is output and 1 is input. IO_in has this data coming from outside through the I/O pad if it is configured as an input pad. IO_out drives the I/O pad when it's configured as an output. As the timer uses the I/O pads to drive an external 7-segment display, the 12 I/O pads will be configured as output pads by connecting each IOB to zeros and connecting IO_out to the timer 7-segment and digit enable ports. IO_in will be left unconnected, as they are useful only when the corresponding I/O pads are configured to be input. So we only need WB_CLK_I, WB_RST_I, and 12 GPIOs. So we can.
Okay, so let me pause there for a second. I'm just going to recap some of the key points. I'm going to back up a little bit because this example that we're watching, they don't connect to the wishbone bus in this design. It's a simplified design that doesn't use the wishbone bus. But for your designs, if you are connecting to the wishbone bus or to the logic analyzer probes, you can see all the interfaces here right now in this bit, right? So all the wishbone signals are here at the top of the instantiation here. So you'll see wishbone clock and reset, and then you'll find the rest of the signaling for the wishbone bus kind of just below that, all the way through down to the acknowledge and the data out. So those you need to connect to interface if you're implementing registers in your design that you want to access from the management area or management core CPU, right? The logic analyzer probes are just below that here. So this LA data in and LA data out are the input and output signals, and then there's an OEB enable. It's an OEB enable signal, very similar to the GPIO, which we're going to talk about future. But that basically is controlling the direction of the signal. I believe actually in the lot, you can look in the details of the logic analyzers, but there's no hard logic around that. So you can use these signals for the most part fairly independently, as long as you're matching the input outputs correctly. But again, double check the documentation on that to ensure that, and also run simulation to make sure things are working the way you expect them to. And then finally here, the key piece here is the GPIO pads. So connections to the GPIO pads are done through a set of 3 signals to each pad, 1 input, 1 output, and 1 OEB. And it is very important that if you are using any of the IO pads, that you connect to the that you drive the OEB signal appropriately. So if you're going to use a pad as an input, then you need to set the OEB signal to drive it high, right? To enable that signal to be used as an input. If you're using it as an output, you need to drive it low. And if you're using it bidirectionally, you need to control that OEB signal based on the signaling you're driving through the pad at any one time, right? So you need to provide logic for that. But those are the ways that you connect. There's a total of 38 pads, right? So 0 through 37. There's vectors for each of these signals that basically map to each of the various IO pads. And then there's RQ signals here. Again, you can find more documentation of that in the if you're interested in using that functionality. Okay, so I think that's the key pieces here for integration.
IO in will be left unconnected.
I'm going to go
in 12 GPIO. Move the ports that are not available. Elections related to the physical.
I think that's probably sufficient on that one. I'm going to go to the next step, which is the other thing you're going to want to do in addition to integrating your RTL into the wrapper is to set up the power on defaults for the GPIO pads when we initially power up the system, to kind of align those to how you're using the pads in your particular design. So there's a video on that, which I'll briefly touch on. That walks through.
First, navigate to the Verilog RTL.
Oops. Okay, so let me back up a little bit.
The Verilog RTL user-defines.v file. In this file, you will find a set of predefined default configurations. One set of default configurations map the corresponding GPIO to the user area, while another set map the GPIO to the management area. The user area configuration values begin with GPIO_mode_user, while the management area configs begin with GPIO_mode_MGMT. Within each of these groups, there are configurations for setting the GPIO as digital input, output, or bidirectional signals. For digital inputs, termination can be set to either pull up, pull down, or none. GPIOs can also be set up for analog mode. So we are going to scroll down to the GPIOs we're interested in. In our RTL, we use the GPIOs from 27 to 37 as outputs. So we need to define those as GPIO_mode_user_standard_output. The other GPIOs are not utilized in our design, so we can just define the rest as GPIO_mode_management_standard_input_no-pull. Note that every GPIO configuration needs to replace the GPIO mode invalid setting with a valid configuration mode, even if the GPIO is not used. Lastly, we can see in the user-defines.v file that we cannot define the GPIOs from 0 to 4. Those IOs are used by the management area and are recommended to not be used except if all other GPIOs are utilized. Also, if we use these GPIOs, we will have to configure them using the firmware, as we cannot define their default configuration here. Finally, GPIO 5 and 6 are mapped to the UART in the management area. We also recommend not using these GPIO pads unless necessary.
Okay, so again, this is there is an RTL file in the template for user project wrapper that basically is used when you run kind of final tape out integration. it's used for setting the power on default value mode for each of the pads, and recommend, obviously, while you can reconfigure those pads at runtime and change the mode, we recommend getting those set correctly based on your design to assign them to either inputs, outputs, or however you're using your those pads. Again, also recommend that you avoid the first 4 or 5 IO, 0 through 5. Those again are used by the management core. So if you will, can run into, it's just more challenging. You can run into conflicts because of the dual use of those particular pads. So if you can avoid them, please, I would recommend doing so. The other ones I would consider avoiding are IOs 5 and 6, because that is tied or mapped to the UART on the management area. And if you're using the UART at all for input and output, or getting or debug or whatever, then it's going to be a lot easier if you're not dual purposing those pads in your design. All right, we pause there for a second, just see what other questions we have. Okay. I'm just going to run through a couple more from the top where I left off. Okay, can I run TinyML or similar software stacks on Caravel? You want to answer that, Andy or Mohammed?
So it's a 32-bit microcontroller, RISC-V, and it is possible to target 32-bit RISC-V using TinyML today. It would be hard and not super high performance. I would suggest that if you're going to do an ML load today, that it would be interesting to build an accelerator to do it rather than trying to run it through the CPU. But you should be able to target a RISC-V CPU from the TinyML software stack today.
Okay, how do we use OpenLane 2 for the contest? Is it compatible or to be used with Caravel GDS 2?
Currently in the middle of an unadvertised beta to the anonymous attendee. And so we're not seeking very large traction on OpenLane 2 on the path to this AI contest tapeout. You are allowed to use it, and it is compatible absolutely with Caravel GDS. So the answer is yes to both the questions. But I would advise to the community at large that I'm not seeking, or we are not collectively seeking, a whole load of people jump on the OpenLane 2 platform for this takeout.
Yep. Good. So next one, is it possible to connect the chip to a high capacity RAM chip?
And you could put an external RAM on the board.
Yes.
And the challenge will be the IO connections between this chip and that chip. And the other possibility is to use a chip connected through serial interface and use that chip to interface to a large capacity RAM. So there are ways of getting a large capacity RAM interface to the chip if you're looking to do something that involves moving a lot of data through the chip to, example, show that an accelerator works. And the simplest of those is to use a serial connection between Caravel and another microcontroller that has a large RAM interface.
Okay. What things other than the RTL are needed to go through the whole flow?
From your calendar,
Alexa, stop.
/website.
Sorry about that. So I think I don't know. I'm not aware of anything other than the RTL. So I think your primary goal for this contest, right, is to generate the RTL using Gen AI. Once you have that RTL, completing the integration and physical implementation of that, which we're going to go through here before we finish this video sequence for the webinar. But that is the primarily what you need.
So three things: you've got to get the RTL, you've got to define the power connectivity, which is default unless you're doing something unusual. You've got to do the user IO config, and you've got to hook up the OEBs.
Yeah, definitely hook up the OEBs. Now,
So the RTL, the user IO config with the power supply and the OEB connectivity, and that with that basic information, you should be able to get the flow to run.
Okay. Given time, I'm going to continue here since we're getting close to the top of the hour. I'm going to continue with the next step here for which I'm going to quickly touch on simulation and show you kind of the example and the infrastructure that we have. You can probably wade into that a little bit deeper by watching the video on your own, but at least I'll give you an introduction to that so you can get where to go and how to get started. You have other options for simulation besides what we're going to show you here using CocoaDB. And then, but the key point I'd like to get to then after that
going into an office.
Sorry, is going to be physical implementation. So we'll go through that kind of next. So just a little bit on RTL verification.
Working 50 hours a week, having that structure.
Okay.
Now that we have,
again, this video is going to highlight an example of what we have set up as an example, and this uses CocoaDB as the framework for running simulation.
our dependencies installed, let's move on to discussing our testing strategy. In this tutorial, we'll be focusing on monitoring the timer outputs, since it doesn't need any inputs rather than the clock and reset.
So this is a little bit longer video, so I'm just going to kind of hit a few key highlights in this. So the video is going to walk through implementing the test bench. In this video, you'll find a diagram that basically provides you kind of the structure for what's being implemented. This is all being kind of implemented in Python, right? For CocoaDB. So they're implementing kind of a monitor function and then a checker to confirm and verify the results. Those are then connected to your daughter device under test. And then it's going to walk through kind of the connectivity of that, kind of how to connect that and run that, and give you an example of how that is implemented. CocoaDB is part of the tool set that you get when you run setup. So when you saw that earlier step we did where you said make setup and it runs and it gets openly, but it also gets kind of tools for running simulation as well. So so you can take a look at that a little bit more depth. There are other options as well for running simulation. And again, depending on what you're doing for your flow, you may have your own process for verifying functionality of your own RTL. There is and we do recommend running simulation with your design integrated in Caravel so that you can ensure that everything is connected up correctly and integrated correctly. And the documentation does talk about how to do that, right? Or it provides an example of how that's done. Okay, so again, I'm not going to spend any more time on it right now, just because I do want to make sure we get through the physical implementation step. Right. So let me jump to that.
In the previous video.
So this is going to walk
now let's
through
begin.
Now using OpenLane to implement the design. Once you have your kind of functional, you have your RTL design and you have completed kind of functional verification of that.
And with the first step of hardening our design, we already changed user project example to user project timer, which is our design. We should now open the OpenLane folder and rename the folder using user project example to user project timer. We can also change the base user project example.stc file to the base user project timer.stc for consistency.
So just to give you a note here, the example, the template provides an example configuration for running for implementing a macro, which is kind of what we're leveraging here. It also that comes with a base kind of a constraints file that would be sufficient for most designs for many designs that are just dependent on the core clock. That are using the wishbone or the core clock within Caravel. If you're doing something where you have timing dependencies that depend on the core clock, but kind of outside of your chip design, there's a number of scenarios where you're going to potentially need to go back and review and update or adjust the constraints file. Again, depending on the specifics of your implementation for your design. So we can probably, again, do a little bit more of a follow-up on that, because that gets to be a little more, there's a little more of a conversation around that in terms of when that happens. But for these simple designs that you're seeing here, the constraints file does not need to be updated. and can be run kind of as is with just some simple modifications, which we'll show you in this video.
Then we start editing the configuration file for the project. The file is at OpenLane user proj timer config.json. First, we will change the design name to user proj timer and the base STC file to base underscore user underscore proj underscore timer.stc. Second, we need to add our Verilog files to the variable for Verilog underscore files. First, user project example.v is now user proj timer.v. Second, we need to add our timer Verilog file. Now let's consider the macros die area. We are going to choose a macro die area of 200 by 3000. The 3000 will span the IOs from 26 to 37 on the left, and the 200 will span the WB ports from the bottom when placed on the left bottom corner in the user project wrapper. This can be visually understood when we take a look at the layout after implementation. So let's edit the die area to 00, 200, 3000. To configure the IO placement, we can change the order of the pins in pin_order.config, which can be found in the OpenLane user proj timer directory. This configuration file syntax is as follows. #S means the following pins will be placed on the south. #E means east, and so on. First, we can open our Verilog files to review the pins. We have the wishbone clock and reset signals, as well as IOs 0 through 11. We're going to place the wishbone clock and reset on the south, and since we connected the pins from 0 to 11 in user proj timer to the IOs 36 to 37, we need to place the IOs 0 through 11 on the left in reverse order, so that pin 0 is at the top and pin 11 is at the bottom. To do so, we can edit the IOs to be ordered on the west using #W, and we can add R to make it #WR, so it will be ordered in reverse. Then list the IOs from 0 to 11. Now we can start running the design using make user underscore proj underscore timer in a terminal in the root directory of our project. After a couple of minutes, hardening the macro has finished. As we can see in the terminal, there are some warnings, so let's check the warnings one by one. First, there are 16 warnings related to linting with regards to the Verilog RTL. Those can be reviewed, but they do not prevent us from completing physical implementation. Second, there are 4 warnings with standard cells that were black boxed during STA. The 4 standard cells are physical cells that have nothing to do with STA, so they can actually be black boxed, and there is no issue. Next, the variable vSource_loc files is not defined. This file is used in IR drop analysis, which we are not reviewing at this level, so that's okay. Lastly, there are max fanout violations in the typical corner. Those are okay since there are no max cap or max transition violations. Generally, max fanout is a soft constraint that can be modified or waived. Now the macro has been hardened successfully. Design is also LVS and DRC clean since it didn't fail in the flow. We can check the antenna violations in OpenLane runs, last run folder, reports, sign off, 43-antenna_violators.report. But there are none, so that's great. Now we can harden the user project wrapper, which will have our macro, and this is what will be integrated into Caravel. So let's go to the OpenLane folder, user project wrapper. First, we will edit the config.json file. We need to change the macro variables to point to our newly hardened macro. Verilog files black box should point to the gate level net list of the user proj timer that we recently hardened. Same goes for extra lefts, extra GDS files, extra libs, and extra spefs. Second, we need to change the macro placement position to mprj1515n, so it is at the bottom left corner, which is closer to the IOs. You can find the macro.cfg file in the OpenLane/user project wrapper directory. Finally, run make user project wrapper. Now, the user project wrapper has also been hardened successfully. We don't have
Okay, so it's just going to run complete and then kind of review the same kind of warnings that we kind of saw previously for the macro, the sub macro, in the design. So again, just at a very high level, what we would walk through or showed here is a updating the configuration file. So there's a config.json file. So within, well, first of all, let's start in your project group. There's an open lane directory. That's where all the configuration information is. And there's going to be one subdirectory for each macro that you need to harden within your design. There's going to be one macro called user project wrapper, which is the top level macro that gets integrated into Caravel. That has to be named user project wrapper. You can't change the name of that. And you cannot change the top level instantiation of that macro, right? So that is, and so basically what that will do is if you depending how you implement your design, you can flatten it and just run everything kind of at that level macro, or you can, as in this example, implement a sub macro that hardens your kind of logic separately and then gets routed or implemented in the top level in a separate step. If you do the latter, you're going to run each of those macros separately, starting with your sub macro and then finishing with the top level macro. And when you go to configure your macros, there's a config.json file that basically provides all the parameters for the flow. Within that references a couple of other dependencies. One of those is a constraints file, an STC file. Again, for many designs, you won't have to modify that file specifically, but for some cases you do, and we will cover that separately in another topic or another subject or another follow-up. There's also some pin order, which you can again go back and optimize kind of the pin placement of your again, you'd want to do this for your sub macro as you're considering how that gets wired up and routed in the top level. So you can configure, adjust and update the pin order and placement around for each of those pins. And then similarly, there's a macro config, which kind of defines where your sub macro gets placed within the top level macro for user project wrapper. So those are the primary things you need to pay attention to, and then when you run, you're generally going to be running looking for a successful completion and reviewing any warnings that might pop up during the flow. Again, if you're running into challenges with any issues in particular, there is documentation, of course. There's also our Slack channel. There's a number of users that have a lot of experience running the flow, will answer questions and be happy to answer questions. And of course, we're monitoring that as well, and we will be answering questions that you might have as you run through that flow. We'll run into any issues. Okay, so from there, I'm gonna stop that piece and go just kind of the final steps. So again, one of the other steps there's additional steps you can consider here in terms of, again, going back and rerunning simulation using your gate level netlist that was produced as part of the physical implementation. That gate level netlist will be in a directory called Verilog. It'll be under the Verilog directory at your project root under a subdirectory called GL for gate level netlists. But we have examples of how to run this example project with the gate level netlist produced after implementation or a physical implementation. There's some additional sign-off review that she can do as well to confirm that that your project has completed any of the timing sign-off constraints or other sign-off constraints as part of the final implementation of your project and integration with Caravel. Once you've kind of gone through that, I'm going to go back to the kind of the list of next steps. I'm sorry, wrong. So once you've done that, you're going there's some videos that then kind of walk you through the steps for uploading your design back to the repository that you created or uploading your design to the Efabless platform, and this all uses Git. So it kind of leverages the same Git client that you're using when you cloned your project. You're going to be creating and adding a repository on the Efabless site. and then using Git to push your design to that repository. And then there's another video that walks through submitting pre-check and tape out jobs once your project has been updated and loaded there. Part of the uploading your design is you're going to the first time you do this on the Efabless platforms, you need to create an SSH key for that is specific to kind of the desktop that you're working on. So that SSH key has to be installed on your local desktop where you're working, and then and that needs to be installed into your account on the Efabless platform. So these 3 videos kind of walk through all those steps. I think we're a little bit over our planned time for the webinar, so I don't know, Andrea, if you want to. I'm gonna suggest we probably don't try to cover that, given kind of where we're at on time, but we can do another follow up to kind of cover that in more detail, or obviously we'll answer questions as people are trying to work through that through Slack or through email at shuttle@efabless.com.
Yeah, I think
good.
I think we should take a crack at some of the unanswered questions very quickly if we can.
All right, sure.
And then I think Andrea's got a poll she wants to put out to the community as well.
Okay, great.
Okay, I'll launch the poll because that's going to only take about 30 seconds.
Okay, great. So you should see a poll up now, right? In terms of just kind of polling for your interest in submitting a design. So appreciate your response on that. In the meantime, let's go through a couple of questions. So going back to where we left off. Implement RTL. I'm trying to figure out where the last question is. Okay, so I think the next question was, can we get the clock to queue timing to determine setup and hold timing?
Yeah, questions about where's the timing report?
Okay. So the timing reports we have some videos I'm going to be posting that kind of walk through that specifically and reviewing the timing reports. So why don't we'll take that as a follow-up. But the reports do exist in the run directories in OpenLane. So after you run that make user proj or whatever your macro is, or the final user project wrapper, within the run directories under OpenLane, that OpenLane directory we were looking at, there'll be a whole set of reports for the various steps, including timing, including timing analysis, static timing analysis.
The default is a fairly small set of corners, but the flow is enabled to run a very large set of corners based on the way it's enabled.
Okay, can we implement an RTL which has separate modules like the top module, bottom module, etc.? Yes, so that is absolutely, you can do that. You can decompose your design into multiple modules. The example we just kind of walked through had a 2 module, like has a top level module and then a separate sub macro. So you can implement, I'm assuming you're asking if you can implement your design in multiple macros. Obviously module wise, or from an RTL perspective, you can have multiple modules and those can all be implemented as a single macro in physical implementation. So both are possible. Okay, can the chip receive data through the SPI protocol? Yes, there is a master SPI controller as part of the management area. You can find more details on that in the documentation, but you can utilize that for data communication.
And there are several examples of open source UART and SPI RTL that you could put in the user project area if you wanted that as an alternative as well.
Implement your own as well. Yeah. Okay. Is there a reference video that goes through the whole flow? Yes. For a first timer, yes, I would recommend the sequence of videos I'm showing you here. So again, this set of videos combined with this set of videos here that implement an example design from scratch. Okay. Does user project implement wishbone slave port logic or directly connect register SRAM ports? does the user project should implement the wishbone? So you're not required to implement a wishbone slave port, but obviously that's an option and a useful one if you want to be able to connect to registers within your design.
If you want to use the wishbone port, you need to create the slave port logic. So you need to create the wishbone to register interface. And I will say that creating a version of the wishbone to register interface takes about 3 lines of prompt with generative AI. So it's not a hard problem. And it's usually correct because there's many, many examples of the wishbone interface in the public domain at this point. And so Raju, if you are struggling to understand how wishbone works, I would take a look at maybe the very first video that I put out, or one of the other videos that's online on generative AI for implementing. It is quick to implement the wishbone interface in Gen AI, certainly with ChatGPT.
And there's a number of project examples too that you can reference and see existing implementations.
Virtually, I'd say 30% to 40% of the user project examples that are online have that wishbone slave interface already implemented in MinRTL. Any large digital design has it.
Okay, so it's next question is assuming I am making wishbone slave area in the user area, what constraints should I consider for load capacitance, max delay values, etc.? Is there an example available for such slave synthesis as reference?
Yes, there is, and the default constraints are actually in, I believe, I'm going to check this afterwards, Samarth, but the default constraints are actually already in by pin for each of the pins on the logic analyzer interface to do that synthesis correctly and be able to work across the interface. So the STC and the timing constraints should both be there by default for you to use.
And the wishbone bus interface as well,
And I'm going to confirm that offline afterwards. I've already taken it out.
Yeah, so generally, so I will I'm cautious about wading into a deeper, more complex conversation of when you need to modify the constraints. But for the base case, you should not need to be able to do that. If you're just implementing a wishbone bus slave interface in the project area. Okay, so last time we tried, there were problems running OpenLane on ARM Linux, Ubuntu 22.23. As far as I can remember, the Google library was not compiling, did not have any artifacts. I don't have any specific info on this specifically, but Salim, but if you want to post this to Slack message, we can follow up.
Yeah, can you put this one in a shuttle@efabless.com email, please, Salim, and we can follow up immediately and try to understand the issue better.
Thank you. Okay, great. So next one, while using AI for RTL generation, can I ask AI to use other existing open source tools like Rockchip from, I guess that's the Rockchip from Chip Alliance to generate the specific SoC?
There's no current barrier to using other tools that are open sourced. It is open access at low cost, or open source tools are absolutely open to be used. We've used iVerilog multiple times in multiple other solutions to do verification as part of the flow through the AI. And yes, you can call other tools. And in fact, we fully expect you to call other tools as part of that flow if you're going to build a complex solution.
Okay, next one is Ryan. It says, does Efabless have a list of macros that haven't been silicon proven? A list of macros that haven't been silicon proven, like the types of RAM you mentioned earlier. That'd be great if someone worked on design, had a chance to be taped out. Yes. So yes, we are actively working on posting and making a set of macros or IP available that can be leveraged in your design. They are not silicon proven as you.
He asked a different question though. He asked, could you tell us the ones that could use work? And the answer is yes, Ryan. So both Mohammed Shalan and I are working to try to generate the list of queued work. So the set of things that we need help on to move the community forward faster. There's about 10 IPs that we need immediately help on. And 2 people are trying to tackle the SRAM right now, but there are many other blocks that we need help on. And so I'm actively working with Mohammed to try to get that list out to the community. And we will put it up on the general channel as soon as we have the list available, and probably also on the announcements channel.
Okay, I am that's so a comment at the end about appreciate. Oh, actually, a couple more pop in and send it late, so we got just kudos for a guy, for us. I appreciate that. Thank you. Can we share our errors we receive on some Slack channel for get guidance along the way? Absolutely. I'm going to share. In fact, let me show you that right now. So if you can encourage you to join the Open Silicon Slack site. This is the Generative AI Silicon Challenge channel, where I recommend you please join if you're participating in the contest, and you can absolutely post questions, errors, ask for help there. There's many other channels, of course, as well that you can participate in and find information that's already been posted and asked and answered there. That might be helpful as well. So
we have many people actively monitoring the Generative AI Silicon Challenge channel. And so if you are having issues there are many people on the Slack channel themselves, other contributors and contestants will respond. And if you don't get a response from them, you'll get a response from the Efabless team. So we're actively trying to understand and help everybody use the tools.
We'll make sure the email follow-up with this video includes a link to Slack, but also there's one on our homepage here. If you want to join, if you haven't joined already, you can join right there by clicking on that and following the instructions to get an invite for that site. Okay, where am I at? Repo following or so. Sorry, I'm new to AI. Is there a repo where I can learn how to use it? Is there a repo for it to Gen AI specifically?
The best one is probably the winner from the last contest. So if you go to the website, Jeff, and pull open the contest page for the results for the last round.
Yep.
And I think
if you go to the current post, there's a link here for the first contest, and on the first contest we post the
GitHub repositories are there,
including the GitHub repositories.
And so that will show you, some extremely complete, very, very well documented examples. And there's a big range in terms of the complexity for those three designs to Samarth and the complexity of the method that the people followed. If you're looking to try to get involved and understand how to get involved, the third one is probably the easiest to follow. And if you think you've got the world's best AI methodology and you're willing to try to challenge Hammond on the top spot, then I would look at the top one and understand what he built. He built a software flow that sits on top of ChatGPT and basically has a closed loop methodology to develop RTL on top of the AI. And so there's a big range of scopes there, Samarth. The bottom one is the easiest to follow to get an introduction.
Okay, great. Last couple of questions, Ryan, following up, asking around how we can help out on the open source IP. So we're happy to get your help. And if you want to reach out to shuttle@efabless.com, we will get you connected.
Yeah, I just wrote you are signed up. And if you send the email to shuttle@efabless.com that Jeff just requested, we will get you connected and get you connected to IP where you feel you can add value.
Super. Analog compatibility, not for this. Well, I don't know if you have any comment on that, Andy, in terms of this particular challenge, right? But obviously for ChipIgnite, we are doing work to enable more, kind of complete analog flow and capability. We'll talk about that probably in a separate webinar.
Yeah, same. So, Caravan obviously enables analog design. You can do analog design inside of Caravel. Although restricted by the I/O in terms of what you can achieve, you can't get very high bandwidth stuff onto this GPIO functionality for some of the pins. We are absolutely open to an analog design submitted in Caravel, generated or driven through AI. So if you have a methodology that you want to drive, James, we're absolutely open to the idea of a submission. We just haven't had one so far.
And the last question was around recordings from today and yesterday, and we will get those posted here shortly, probably, if not today, by tomorrow. Okay. And that's all the questions we have currently. So I think that might conclude it. Anything else, Andrea?
No, I think that's it, Jeff. Thank you so much. Great session.
Super. Thanks for everyone's participation. Look forward to seeing your designs. Thanks, everyone.
Thank you.
All right. Take care. Bye.